Welcome. Welcome to the third lecture of first week. Today we will discuss on solar radiation and Earth's energy balance, or sometimes we call energy budget. So, with respect to this, we will try to understand that how the incoming solar radiation and how it has a repercussion on our climate change, and how it drives the Earth's climate. So, these 5 points we will discuss in terms of the concepts that those are covered. The first is incoming solar radiation. We will try to understand this as far as the sunspots, as we know with respect to dark spot or black spots, and the solar constant. And secondly, we will try to understand the solar radiation and various interactions that happens in the atmosphere. And then we will go on to understand the annual energy balance, sometimes we call in form of a budget. And then we will talk about the photosynthetically active radiation, which is abbreviated as PAR. And then we will try to understand that how they are related, or they control, regulate, or are attributed to climate change. So, let us try to understand it. The first one is with respect to the total solar irradiance. So, sometimes we abbreviate it as TSI. So, in terms of the total solar irradiance, this particular figure says that yes, the total solar irradiance, that is the energy from sun which is reaching on earth, or we say top of earth atmosphere, that varies between 1365 to 1372 in terms of watts per meter square. So, over a surface area in terms of meter square, this is a average variation, but this variation, let us try to understand why this is. With a solar constant, or we say the mean reference value, we sometimes talk as 1367 watts per meter square. So, if you see the variation which is plotted in terms of a curve, in terms of the graphs and the ups and downs for past 80 years, and then it is following a particular cycle. It is following a particular cycle, and the upper axis of upper x axis, it is shown in terms of the days. That means starting from 1st January 1980, and on y axis the irradiance values, the total solar irradiance values varies between 1362 to 1368. So, it can be seen that perhaps some time back the solar radiation also have touched 1368, it has crossed 1368, and at times it has come down to about 1362 at some part of the year. So, those are a little exceptions, but in an average range they fluctuate between 1365 to 1372. So, this variation in the solar irradiance has a bearing on the climate change. And now, coming to the next aspect is the sunspot, the dark spot, the black spot. We all know it. We all have studied this in our high school days. And then this particular curve here shows the number of sunspots. On the y axis, the number of sunspots have been mentioned, and on the x axis, the year. So, if we go back to 1600, that means about 425 years back, and try to plot it, the number of sunspots, we can see it is going as high as 270 or 280. If that can be seen from the plot, sometime around 1955, the maximum number of sunspots have gone beyond 270. So, what we are seeing from here, 3 different types of minimum or minima. So, Maunder is the first one who actually have tried to study this. what he has studied, that during 1645 to 1715 there were very less sunspot activity. He named it after his own as that phase as Maunder minima as far as the sunspot scarcity is concerned. And then if we move on to the another low sunspot activity phase, that is between 1790 to 1830, and that is again mentioned after another scientist named as Dalton. So, as Dalton minimum during 1790s to 1830, and then we have a modern maximum. So, in contrast to these minima, we also have found a kind of a maxima around 1915 and beyond that. So, that phase maximum number of sunspots have been registered, and that phase has been called as the modern maximum, where high sunspot activities have been registered. And so, the solar cycle, that means the variations of magnetic flux on the sun's surface over time. So, this sunspot cycle, we have studied that in an average of 11 years the cycle, but it varies between 18 to 14. So, the average we in a general sense we remember as 11 year cycle or 11 years epoch. Now, let come to the next understanding with respect to the latitudinal variation. Friends, all of us know the shape of earth, and we have the biogeography, the equator, then you have the Tropic of Cancer, the Tropic of Capricorn, then you have North Pole and South Pole, and the tilt of 23.5, that is again between 22 to 24, but these days it is around 23.5 degree as far as the tilt is concerned. So, what is happening? This shape of earth, the tilt or the inclination of earth is allowing the earth surface to receive variable solar radiation. So, the sun solar irradiance what falls on the earth surface is not the same all across the exposed surface. So, what happens in the tropics, the earth receives maximum, or you say the surplus solar radiation or solar irradiance. So, the radiant energy in terms of a 1 year scale has been shown here in this particular figure, and this implies that we have a surplus between plus or minus 38 degree latitude. So, north and south 38 plus and minus we usually consider. So, we have a surplus of radiant energy received over our surface, and a balance exactly at 38 degree both on the northern and the southern hemisphere, and then there is a deficit beyond that. There is a deficit beyond 38 degree latitude in both the hemispheres. So, how this is? Because we have the the transfer of heat. So, this heat transfer phenomena allows the movement or transfer of heat from tropics to the non-tropics. So, beyond 38. So, that is how the heat is balanced, it is transferred. So, this is very important to understand that poles they lose energy, tropics they gain, and at mid latitude around 38 degree centigrade these incoming solar radiation is balanced. So, energy imbalance does not cause constant warming or cooling, because heat shifts polewards via to both the north and south poles via oceans. You have wind and various latent heat exchange processes, right. So, this is what explains us the latitudinal energy balance. Sometimes we say imbalance. So, imbalance and then it is getting balanced because of the transfer phenomena. So, this talks about the latitudinal variation. Now, let us move on to the next concept of transmission. Friends, the atmosphere is not transparent. It has some selective transmission behavior. So, 70 to 75% of the sunlight reaches, and the surface, from the surface 15 to 30% the longer wavelength infrared radiation escapes back or to the outer space. The visible lights, they passes easily. UV and IR are absorbed. Greenhouse gases such as we know, carbon dioxide, methane, nitrous oxide, ozone, these gases, they trap the outgoing longer wavelength radiation, infrared radiations. And then we have various scattering processes, Rayleigh scattering, Mie scattering, and all those things. This scattering, they affect the blue light. In turn, it affects the incoming solar radiation. So, this interplay drives the greenhouse gas effect on Earth's energy balance. Look at the diagram which is shown in the left hand side of this particular slide. On the left hand side, the upper one talks about, in the y axis talks about the spectral intensity, whereas on the x axis it talks about UV, visible and infrared. So, in terms of the UV, visible and infrared, we can see that the red color there implies or indicates the downward or downgoing solar radiation, which is about 70 to 75% in the visible UV, the late UV, the whole of visible and part of the near infrared and some part of the middle infrared. But when you go to the far infrared region, you have lot of upgoing or outgoing thermal radiation, that is about 15 to 30% as I just mentioned, that escapes to the outer space. In terms of percentage of total absorption and scattering, the next figure talks about or depicts in terms of percentage how much is the total absorption and scattering. So, we can very well see the filled and the unfilled one, or the gray was or the gray shade and the transparent or the white portions as far as the absorption and scattering portions are concerned. And then if we divide them into various components, the major components are water vapor, carbon dioxide, oxygen and ozone, the methane, the nitrous oxide and the Rayleigh scattering. And you can see lot of this is happening because of the presence of water vapor in the atmosphere. So, you can see lot of water vapor are present during the summer season. So, that time the scattering phenomena and absorption phenomena may be means totally regulated by the presence of water vapors. Similarly, the carbon dioxide and oxygen and ozone, and then the Rayleigh scattering, nitrous oxide and all this. So, these gases, the presence of these gases and all of them are the greenhouse gases. The presence of these gases have an important repercussions, have an important bearing on the transmission or the radiation transmission process. Now, let us move to the next concept which talks about or which discusses about PAR, the photosynthetically active radiation. So, what it means? Friends, the earth, our own planet earth is very unique. It is unique in the sense it has biota. It has the plants, animals and microbes. The plants, they trap the incoming solar radiation. In turn, they convert the light energy to chemical energy. This is the unique property which earth has because of the presence of the green pigments, that is chlorophyll, that allows the plant material to trap the incoming solar radiation and convert it to chemical energy in the process of photosynthesis, and in turn it releases oxygen, it regulates the transpiration process and many things. So, friends, this part of the electromagnetic spectrum, the light is absorbed from the entire visible spectrum when all pigments are combined. So, what it means? This part of the electromagnetic spectrum, we all know the total electromagnetic spectrum starting from cosmic ray, X-ray, gamma ray, UV visible, then you have microwave and the radio waves. So, in this part where it is between 390 to 760 nanometer, this part of the electromagnetic spectrum is in the visible range. There we can, our eyes are sensitive to visible range. So, we can see things at in the visible part of the electromagnetic spectrum, all of us know it. So, this part of the electromagnetic spectrum mostly in the visible range is active for photosynthesis. So, that is why rest of the energy is not utilized for photosynthesis, only this part of the electromagnetic spectrum which is in the visible range do participate in the process of photosynthesis, and that is why this is called, or this part of in this part the radiation which is received are called photosynthetically active, abbreviated as PAR. It is a very important things we will again be discussing perhaps in future, but we have a lot of when we calculate PAR, we take it to model how much is the photosynthesis or how much is the carbon withdrawal from the atmosphere by the process of photosynthesis. So, this is a very important concept as far as PAR is concerned. Now, let us look at a few of these expressions numericals. All of us know in terms of the Earth radiation budget, the flux of solar energy arriving at Earth, that is solar constant represented as SO or S0, is expressed by this formula Q upon 4 pi by R square that we just understood, which we calculate, which show that it varies between 1365 to 1370. So, in an average we call it 1367, that is the solar constant in terms of watts per meter square and expressed using this equation. Next, move on to the incoming shortwave solar radiation, that is expressed by E solar S0 pi and sometime we call it A square. So, what it is? It is the radius of the Earth, or it is the surface which is facing the Earth. So, you take pi A square, that means the whole surface that is exposed to solar radiation at any point of the day is taken care through this equation. So, that pi A square talks about or takes care of that. The absorbed shortwave solar radiation is expressed by E solar absorbed 1 minus this alpha. This alpha term we know as the planetary albedo. I am coming to that, and S0 pi A square. So, what is this alpha term, the planetary albedo? By default many times we take it as 0.3. Friends, what happens? Albedo is nothing but the reflectivity property of our surface. So, when solar radiation falls on this, how much lot of it get absorbed and many of it get reflected. So, how much it is reflected? We have different cover as far as the Earth is concerned. We have glaciers, we have snow cover, we also have vegetation, we also have the blue dark water bodies. So, dark water bodies absorb a lot, snow and glaciers they reflect a lot, and the deserts, the clean areas or the barren areas, they reflect a lot in comparison to the other or the counterpart as far as the vegetation or the wetland or the water bodies are concerned. So, in general the planetary albedo alpha is kept as 0.3, which makes about 30%. If the Earth emits like a black body of uniform temperature TE, then the Earth emission radiation or Earth emit radiation is calculated using another formula which is there, that includes a term and a constant coming from Stephen Boltzmann. Since the absorbed solar radiation is equal to the emitted radiation, then the planetary emission temperature is what we are getting is about this in terms of the TE. So, which is expressed using this formula. I am not going into very details of this formula, but for the sake of our understanding calculation how it is done, I have put it here and trying to discuss with you. So, estimation of the averaged incoming solar radiation E solar per unit area is expressed using this expression E solar upon 4 pi a square. So, finally, S0 upon 4. The incoming shortwave solar radiation, then coming to the observed shortwave solar radiation. Since the observed solar radiation is equal to the emitted solar radiation, the planetary emission temperature is expressed using the last but one formula. So, in turn the mean atmospheric temperature is also takes the expression of epsilon oblique 2 to the power to the 1/4 of its power of the surface temperature. So, these expressions are useful when we try to calculate the various the in terms of solar radiation received over certain area of emission certain area over certain conditions. Let us have a look at the next one, that is Earth's energy balance. On the left hand side of this figure, the incoming solar radiation has been shown, and on the right hand side the outgoing longer wavelength infrared radiation has been shown. And as I mentioned before, this is a kind of budget. So, this budget is this budget varies, the quantity varies a bit over time, but this gives us a broad idea understanding that how much is the total in and out as far as the solar radiation and the outgoing longer wavelength radiation is concerned. So, the reflected solar radiation, and let us see, the incoming solar radiation is total is about 342 watts per meter square. Out of this, the at the top of the atmosphere, the solar radiation which is received is about 342 watts per meter square on the top of the atmosphere. Then out of this 342, about 67 watts per meter square is absorbed by the atmosphere, and rest what you say means 67 is absorbed by the atmosphere, another 168 watts per meter square is absorbed by the earth surface. Rest 107 is reflected back to of the solar radiation is reflected back by the atmosphere, which has a share of 77 watts per meter square, and reflected by the earth surface, which has a share of 30 watts per meter square. So, this is with respect to the incoming solar radiation, absorption and the reflectance. But then when this the earth surface absorbs 168, what happens? The various processes are there. So, in terms of the sensible heat and the latent heat, the earth surface loses about 24 watts per meter square and 78 watts per meter square in terms of the radiation from earth surface. Let us move to the next part, that is the outgoing longer wavelength radiation. So, the earth surface is absorbing 168 watts per meter square, and through sensitive heat and latent heat is releasing 24 watts per meter square and 78 watts per meter square. These are not the longer wavelength. Okay. So, now let us go to the emission, which we are talking in terms of the longer wavelength radiation. So, emitted by surface 390 watts per meter square is emitted from the earth surface. Out of that, of this, the clouds, the various gases, particles and other elements in the atmosphere, they absorb. So, they absorb about 3 350. Okay. So, so 350 is observed there and 40 is coming back from this back to the atmosphere. So, now with respect to the outgoing long wave radiation, 235 watts per meter square, this much is going out in form of outgoing long wave or escaping to outer space in terms of long wave radiation, and of it about 235 watts per meter square. So, emitted out of this, the atmosphere is emitting 195 and 40 watts per meter square is coming back. So, this is what in a nutshell, if we want to understand the Earth's energy budget. Now, in terms of the feedback mechanisms in climate change. So, how this is related to climate and climate change? This what you say, solar radiation, solar irradiance and photosynthetic active radiation, the variation across the latitude and the transmission and different what you say energy balance activities, how these have a mechanism as far as the feedback is concerned in understanding the climate change. So, radiative forcing affects Earth's energy balance. So, what does it mean? Positive forcing warms the surface, negative forcing cools the surface. Okay. So, that is why this term positive and negative. It is positive, that means it is warming, and vice versa if it is negative. So, we say negative forcing means it is giving us a cooling effect. So, the feedback mechanism. So, if positive, that means it amplify the climate response, and if it is negative, it dampens the climate response, that means negatively it affect the climate response. So, three categories of this feedback loop. Let us understand. First one is the radiation energy transfer, second is the heat energy, third is the most importantly the biosphere interactions. So, the photosynthetic active radiation part what I have discussed is corresponds to that. Anyway, so let us see the first one, radiation energy transfer. We can divide it into two parts, the temperature and albedo feedback. In terms of the temperature feedback, the Earth's surface emits the infrared radiation or more of the infrared radiation, which negative feedback by cooling the plant surface. So, that means if it is emitting a lot, that means it is giving a negative feedback, that means it leads to cooling. Second, in terms of albedo feedback, melting of ice and the snow and glacier. So, more solar absorption. So, in contrast to the ice deposition, if it melts, that means it will lead to more absorption of the sunlight, and in turn it will warm the surface. So, that is a positive feedback. Coming to the next one, the second one is the heat energy transfer. So, oceanic heat transport distribute the heat as we discussed in terms of the latitudinal space. So, if it distributes, that means what happen? Cool region, positive distribution from one part to other. So, from a higher means tropical region to the non-tropics. So, that means it leads to cooling. So, a positive feedback. Now, let us discuss with respect to the biosphere interactions. It regulates the greenhouse gases, carbon cycling and many other processes. That is how it modulates the warming effects. That means, it has both positive and negative feedback, which we will eventually discuss in our subsequent classes or lectures. So, we have the comparatively in terms of albedo, you have a forest, you have a non-forest. Only from albedo point of view, the forest is a positive or and the deforested land is a negative feedback because the albedo is higher there. But from other interactions point of view, energy interaction point of view, it is a negative feedback comparatively. So, these are the various processes we are going to discuss as far as the biospheric interaction is concerned, so as to understand the feedback mechanisms in climate change. Now, the following references have been used for discussion of this class or this lecture. So, how do we conclude? We conclude with these points. I will read it out again. Earth's energy balance is the equilibrium between incoming solar radiation and the outgoing terrestrial radiation or the longer wavelength radiation. The 30% of solar energy is reflected by atmosphere, while rest is contributing towards warming of the earth or earth surface. So, heat is redistributed across latitudes by ocean, wind and various heat exchange processes, latent heat and others. Selective absorption of gases warms the surface and drives the climate processes. Cloud cover, surface albedo and seasonal solar variations significantly affect energy absorption and the radiation balance. And disruption to this balance, such as increased greenhouse gas concentration, which is happening at a faster rate because of anthropogenic induced causes, human driven causes, they drive the climate change and global warming, and more so it is happening at a very faster rate. So, many more of this we are going to discuss in our subsequent classes. Thank you very much for attending this. Thanks a lot.